Okay, well, welcome to this lightning lecture session. We have 5 presentations, which are allowed 5 minutes each, and we'll try and do this fairly strictly. There's a timer which the lecturer will be able to see, and also when you have 1 minute left, I will stand up and look intimidating. So our first talk is by Abraham Izabella from Brazil, and we're going to talk about relational generalized IFSs. So, okay.
Now, my presentation is concerned with a new generalization of IFSs, relational generalized IFSs. We have a complete metric space XD and a finite family of functions, continuous functions apart from X2 with values in X. And we consider a closed equivalence relation R and X. We require the functions to be contractions, but not on the whole space, only for those pairs of points, x1, y1, x2, y2, such that x1 is in relation with x2 and y1 is in relation with y2. And the second condition is that each function maps the class of each element x into itself. We consider the following notation. By the class of a compact set, we mean the family of all equivalence classes of the individual elements of space. Then we say that 2 compact sets are equivalent if they have the same equivalence class, and due to technical reasons, we consider the set MR consisting of all the compact sets, subsets of X that are equivalent. The Fractal operator is defined like this in MR. And we also work with this operator GS, which depends on a single variable. So the significant part is that there is compact subset A of necessary distance set A is depends on by GS, and is the limit in the household perimetric of the sequence of iterated GS applied to K. Regarding the speed of convergence, we have this evaluation of the distance between the attractor generated by K and the emitter of GS applied to K. Then we can reconstitute the attractor generated by K by gathering all the attractors generated by the individual elements of K. And the first theorem states that the function which associates a compact set K, the attractor that it generates is continuous. We can extend the class of sequences that converge to the attractor if we start with 2 compact subsets of K1 and K2, which are equivalent. We define the sequence Kn, which turns out to be convergent, and is limited towards the attractor generated by K1 and also by K2. And here we see that 2 compact sets which are equivalent, they generate the same attractor. GIFSs are real extensions of the classical GIFSs. If we consider the total equivalence relation, then we arrive at the classical GIFS. In the second example, we consider this GIFS on R2, consisting of 2 functions, x1 and x2. We say that x from y1 is in relation with x2, y2 if they have the same first component. In this case, for each compact subset A times K, we have an attractor, and we see that it depends on A. And that's it.
We'll keep questions after the type or informal questions you can ask. Thank you. Our second speaker, Aiswarya, from Tirupati. And telling us about nonlinear fractal
Histopolation.
histopolation function. Right, very good. Oh,
So good evening, everyone. So I'll be talking about the construction of nonlinear fractal histopolation functions. So in classical geometry, we approximate objects to smooth functions, whereas in fractal geometry, using fractal functions, we approximate objects to non-smooth and self-similar functions. So histopolation is a technique in numerical analysis where we find functions which has the same area as a given histogram. The property of histopolation functions is that they are neither necessarily continuous nor of interpolatory nature. So recently, Barnsley and P. Vishwanathan defined fractal interpolation functions, fractal histopolation functions. So we are trying to generalize the fractal histopolation functions by introducing Radcliffe contractions to the underlying IFS. So to know what is a Radcliffe contraction, we have to know what is a phi contraction. So if phi is a map on the positive real axis and x is a metric space, then f on x is called a phi contraction if the distance between f of x and f of y is less than or equal to phi of the distance between x and y. Then we further call f a Radcliffe contraction if it is a phi contraction for some non-decreasing function phi, and the function phi of t upon t is strictly less than 1, and this function is non-increasing. So in any complete metric space, every Radcliffe contraction has a unique fixed point. Now we all know what is an iterated function system. So it is a complete metric space with a finite set of continuous maps. And if we have an IFS consisting of Radcliffe contractions, then it has an attractor. This is unique. And now we are moving on to the construction. So we are given with a finite set of points, x0, x0, x1, etc., xn, which are strictly increasing. And then another finite set, which is a subset of the real numbers. And then we denote I as the largest interval, x0, xn, and in as the subintervals. Then we define the maps ln on I as contraction maps, and they maps the endpoints of the interval to the subintervals. Now we have Fn from I cross R to R defined as this Cnx plus dnsn of y plus En. Cn's and dn's and ens are constants. Sn is a Radcliffe contraction. And we have the space of all bounded functions on I with the supremum norm. So we define the Reed-Bajraktovich operator T on B of I as this equation. And then we proved that this T on B of I is a Radcliffe contraction. So it has a unique fixed point and it satisfies this self-referential equation. And then we further proved that the maps Wn's defined as ln of x, comma fn of xy with respect to the metric d eta are Radcliffe contractions, and the IFS consisting of these maps has an attractor, and that attractor is the closure of the graph of the fixed point of the RB operator. Then we proved the Riemann integrability of this function. So we defined alpha to be the maximum of the contraction factors and d to be the maximum of vertical scaling factors. If whenever alpha was equal to d, we assumed that the maximum of contraction factors should be less than or equal to half. Then we proved that the RB operator, wherever the RB operator is discontinuous, that collection of points has Lebesgue measure 0. And for that matter, the function was Riemann integrable. So now we are going to check whether this constructed function will be a solution for the histopolation problem. So we are given with a histogram. So this means that for the subinterval xi minus 1 xi, the frequency will be yi. So we want to check whether when the function f will satisfy this equation basically. So in the subinterval, it should have the same area as the histogram. So we were able to prove that if the constant En satisfies this condition, then the RB operator solves the problem. So instead of taking dn's as constants, we can take them as variable functions also. So in that case, this was the condition. So these are the references. Thank you.
Okay, let us begin by recalling the definition of a possibly infinite iterated function system. So we have a pair with a complete metric space and a family of functions such that the functions are continuous and the family is bounded. That means that for any bounded set, the union of the images is also bounded. With this, we can get our main definition. Oh, no, first, let's introduce the fractal operator. So the fractal operator is defined on the closed and bounded sets, and it's the closure of the union of the images of any bounded and closed set. And we require the second condition here, such that the operator, so that the operator is well defined. So we go again to the bounded and closed sets. And with this, we have our main definition. So a mixed, possibly infinite iterated function system is an IIFS, and we consider two sets I and j, such that for every function in our system, their Lipschitz constants are less or equal than 1, and there exists some a between 0 and 1, such that for any function with the index in I, we have that it is a contraction on the entire space, and any functions with its index from j, we have that it is a contraction, but not on the entire space, just on the closure of the orbit of any point of the space, where the orbit, by the orbit, we understand the union of all compositions of functions from the family indexed by j. So we do not consider the entire family of functions, just the ones from j. And note that we have all the Lipschitz constants less than a or equal than a, which is planetary, so it's less than 1. Okay, and with this, our main result is the following. So if we have a mixed, possibly infinite iterated function system, then the fractal operator is weakly Picard. That means that if we start from any bounded and closed set, we obtain some attractor that depends on the starting set, and it is a fixed point of the fractal operator, and we can recover this set by iterating on the starting set B from where we began. Also, note that if J, the set J from the previous definition is empty, then we have the classical definition of an IFS with just contractions. Okay, let us see some examples. So our first example is composed from two contractions and one orbitally contracted function. And here are some illustrations. So these are the approximations for the first 20 iterations of the fractal operator. We can see that the parameters are chosen the same for both of the illustrations, but the first one starts from the point 1, 0, and the second one starts from the point 100, 0. And as we expect, the images look different because, again, the fractal operator, the attractor of the fractal operator depends on the starting set. And also, we have an example in which I and j are infinite. Here I don't have a picture, but if we start with two complete metric spaces and we have some set in their product, closed and bounded, if we choose I infinite and dense in A, and some infinite set J such that is disjoint from J, we can choose some functions G such that with Fi defined as just the index for any point when the index is from I, and with this pair when the index is from J, then this system can be shown to be an MIIFS, and the attractor is the one we see down here. And with this, we have an example of a set that has I and J input. Okay, that's about it. Thank you. Yeah.
Thanks, Kenneth. So I'll be talking about IFSs with local radial contractions. So what is local radial contraction? We all know contraction. So local radial. So there are two terms, local radial. So we take a point and then we can find a neighborhood around that point such that the function contracts the points in that neighborhood, but you have to take the distance from the radius point to any point, not like any two given point in the neighborhood. That's what this definition says. Is x naught and any y in the ball. So in that case, this type of functions contract, and therefore they are say the local radial contraction, or one can say pointwise contraction as well. So there are some examples of this type of contraction. These are the examples. The first one is 3/4 of the unit circle, and this function contracts in a way that it does not contract the whole space, but to take a point, then you can find a neighborhood such that it contracts, and the second one is also similar. So wanted to study the IFS consisting of such type of maps. So first of all, we need this definition of a rectifiable path, or the definition of a finite path, because the space will be considering is a rectifiably path connected space. So, and also need this example lemmas, and this is a rectifiable path connected space. So this is an IFS with a rectifiable path connected space and finitely many maps, and we consider the code map, and we show that this code map is well defined and uniformly continuous in the symbolic space. So how do we do that? We consider this. As you can see, we can use the lemmas, the previous slide, to show that this holds, and then this one. And so we can show that this sequence is Cauchy, and therefore also if we take any 2 point x naught and y naught, then we can show that this converges, and therefore the limit is independent of x naught, and hence the pi map is well defined. And with this result, we can also say that it is uniformly continuous, and this is invariant. This set is invariant, and it is a unique invariant set due to the this result. Now, we also studied the existence of the invariant measure of such type of IFSs. We consider this space and the Markov operator, and we show that the Markov operator has a unique invariant measure with the help of this lemma. And this is the proof idea. We consider the point mass measure and this sequence, and we show that this sequence is Cauchy in the weak sense, and we show this next step, and hence this limit is in the weak sense, and therefore the an invariant measure exists. And you can trivially show that this is actually push forward measure. So these are the references. Thank you so much.
take a look. Wait. Okay. Cool. Okay, thank you very much. So today my topic is dimensions of projections of typical self-affine sets. This is based on the joint work with my supervisor Dejun. So we first consider L d times d invertible real matrices. And here we always assume that the norm of every Ti is strictly less than 1/2. For fixed translation A, we consider following affine iterated function system. Faix equals to Tix plus AI. By Hutchinson's result, there always exists a unique non-empty compact set Ka, such that Ka is a union of K under the mappings Fai. And we often call the set Ka the self-affine set generated by the mappings Fai. So first we introduce the definition of the affine dimension. Given the linear path T1 to TL, we have the following definition of this affine dimension. Here, this potential function Psi is a singular value function of the linear map Ti. By Falconer and Solomiak results, we have that for the almost all translations, the Hausdorff dimension and the box-counting dimension of Ka are both equal to the minimum of D and the affine dimension. So, okay, let me move to our main goal. We let W be a linear subspace of Rd, and the Pw be the associated orthogonal projection onto W. Our goal is to study the dimensions of the projections of these typical self-affine sets. So for the dimensions of projections of concrete Fractal sets, there are several results. For self-similar sets with dense rotations, for Bedford McMullen copies of irrational type and their generalization, and for self-affine sets satisfying irreducibility and separation conditions, there are various results. And all above results mainly focus on the concrete Fractal sets. And our results mainly focus on the typical self-affine sets. Okay, let me move to our results. So first, we consider an affine iterated function system, Tix plus AI. And we let W be a linear subspace of Rd with dimension K. Let Pw be the orthogonal projection onto W. We define the following value, Tw. Note that the definition of this value Tw is similar with the definition of the affine dimension. Here we change this original potential function Bsti to this new potential function Bspwti. Our first result says that for the almost all translations, the Hausdorff dimension and the box counting dimension of Pwk are both equal to the minimum of K and Tw. And there is an interesting question that if we fix the numbers D and K and let W move among the Grassmannian GDK, what is the number of the possible values of the dimensions of Pwk can it take? Our second result says that this number has an upper bound. The upper bound is equal to this binomial number, Z2 choose K. And actually, this upper bound is sharp. In other words, given any numbers D and K, we can always construct an affine system such that this equality holds. And our third result says that if we suppose that the case exterior product of Ti is irreducible, then the Hausdorff dimension and the box counting dimension of Pwk are both equal to the minimum of K and the affine dimension. So in other words, in this special case, the dimension preserves under the projection map Pw. Okay, let me give some remarks for our results. So the main difficulty with this problem is that this newly defined potential function, Bspwti, is not necessarily submultiplicative. In other words, if we just apply the classical results, classical methods, it may raise some problems. And our proof mainly uses the methods of transversality, ergodic theory, and products of random matrices. And last, besides the fractal dimensions, we can still apply the methods of Fourier transform and transversality to study the big matrix and the integral of the projections of typical self-affine sets. Okay, that's all. Thank you.